Hello students, I am CG sir. In this lecture, we will discuss the algebra of linear transformation. Okay, in the last class, we discussed what is linear transformation and we have seen some examples of linear transformations and some theorems, some few theorems. So, we start with the theorem. Let F be any field and V and W be two vector spaces over the same field F. Let T and U be two linear transformations from V to W. Okay, and C be any scalar. Now we first define that the summation of two transformation is again a linear transformation, and the multiplication with scalar with the transformation is again a linear transformation. So first of all, we define this T plus U. It is also a mapping. Now I am not saying the linear transformation. First of all, it is a mapping from V to W defined by T plus U of alpha equal to T alpha plus U alpha for all alpha belongs to V. So it is a definition. Now you can easily check that T plus U is also a linear transformation. How? It is the easy task. You will take alpha beta from V and C from F, then T plus U of C alpha plus beta. You have to prove it C into T plus U of alpha plus T plus U of beta. So I leave it as your home task. It may be used as the class task. So easy. Next, another transformation, another mapping, Ct is defined from V to W as Ct of alpha equal to C into T alpha. Look, this is the definition. Okay, for all alpha belongs to V. You can again check that this Ct is a linear transformation from V to into W. Now, what we get a collection of linear transformation from V into W. So if we take this collection in a set, along with these two operations, we can prove that this set will make a vector space. Okay, because for vector space, we need these two operations, addition and scalar multiplication. This vector space is denoted by LVW. So LVW, what are the elements? The elements of LVW are linear transformations from V into W. Okay, once we get the linear vector space, we find the structure or the dimension of it, basis and dimension. Let F be a field and V and W are two vector spaces, finite dimensional, such that dimension of V equal to n and dimension of W equal to m. Then dimension of LVW, this space, is equal to mn. We will prove it. This proof is not so hard but little bit tricky. Let B alpha 1 alpha 2 alpha n be an ordered basis of V, and B dash equal to beta 1 dot beta m be an ordered basis of W. Okay, dimension m, dimension n number of vectors, m number of vectors. Now for each pair of integers pq with 1 less than equal to p less than equal to m and 1 less than equal to q less than equal to n. So each pair, so how many pairs will get? M varies over from 1 to m number of q 1 to n. So mn number of pairs you can find 1 1 1 2 1 3 1 m 1 n, similarly to 1 2 2 etc. So for each pair p and q, we define a mapping EPQ from V to W. How? Such that EPQ of alpha I equal to 0 if I not equal to Q, and if alpha equal to Q, this quantity equal to beta P. Okay, so using Kronecker delta symbol, this is equal to delta IQ beta P, because when I equal to Q, this quantity is 1, when I am not equal to Q, this quantity is 0. Now let us check what happens with this. So first consider the transformation E11. it takes the basis element of V, that is alpha 1, alpha 2, alpha n. It takes alpha 1 to beta 1 because 1 equal to 1, that is beta p. 1 not equal to 2, so it is 0. 1 not equal to n, so this is 0. So first transformation E11 takes the basis elements in this way, beta 1 0 0 0. So once we get the basis element where it transforms, we get the total view of this transformation. Similarly, for the next transformation E12 takes alpha 1, 1 not equal to 2, so it is 0. Here E12 of alpha 2, 2 equal to 2, so it takes to beta 1, this will be beta 1. Similarly, E12 of alpha n equal to 0, and this way E1n of alpha 1 0, E1n of alpha 2 0, dot E1n of alpha n equal to beta 1. So here the diagonal elements all are taken to beta 1. Look, in this way we get the n number of transformation E11, E12, E1n with respect to their action on the basis of V. So here we get n such transformation. Next we vary 1 to 2, and this gives you E21 of alpha 1 equal to beta 2, E21 of alpha 2 equal to 0, E21 of alpha n 0, and similarly the others. Here the diagonal elements are taken to beta 2, and in this way we get the transformations E21, E22 dot E2n. Again n number of transformations we get. So the first index 1, next 2, next 3, next dot it will be em1. So m set of n, each set contains n number of transformations. So mn number of transformations, we get the actions of mn number of transformations in this way. Okay, I am showing it, otherwise you cannot understand from only this. So these mn number of linear transformation from V to into W are defined. Now our claim is that these mn transformations form the basis of LVW, because our target is to find the basis of this, and ultimately these transformations will form the basis of this. So how to make it? If this set spans this, spans means spans and linearly independent. So let T be an arbitrary element in LVW. So T, definitely T is a linear transformation. So T takes alpha j to T alpha j, it is the element of W. So the coordinate of this element with respect to B dash, we let this is A1j dot AMJ. J varies from 1 to n. So J varies from 1 to n. Therefore definitely this element can be represented as the linear combination of the basis elements of B dash A1j beta 1 plus dot AMJ beta m for j equal to 1 to m n. Now since we get E11, E1n, E21, E2n, Emn, M1, Mn, there are mn number of linear transformations, we take their linear combinations. There are mn number of transformations, we take the linear combination of this. And since LVW is a vector space, so definitely it will be again a linear transformation. Suppose this linear transformation is named by U. Okay, now we find the action of U on alpha j. U of alpha j equal to this of alpha j plus this of alpha j, this of alpha j. So each quantity in this way. Look here, E11 alpha j, it will be 0 because for a fixed j, and E1j alpha j, that will be beta 1. So from the first this line we get A1j beta 1. Next we'll get A2j beta 2. Similarly from the last line we get AMJ, this will be beta m. Clear? But look at this element A1j beta 1 plus dot AMJ beta m. It is nothing but this. That means T alpha j equal to U alpha j. T alpha j equal to U alpha j. Since alpha j is taken arbitrarily, means we can change alpha 1, alpha to any element. So U equal to T, U equal to T, that means U of alpha j equal to T of alpha j for all alpha j. Okay, so what we get, that means any linear transformation can be represented as a linear combination of the elements e11 dot dot e1n, e21 dot dot e2n, e. We get the idea of linear combination. Next, we have to check that this set is a linearly independent. Here we have proved that T is a linear combination of this. Next, we have to prove this set is linearly independent. For this, suppose U is the null vector. So U is the null vector means this side equal to theta, or U of alpha j equal to theta. Now from 3 means here we get U of alpha j equal to this equal to theta, this equal to theta, this equal to theta. Now beta 1 dot dot beta n, these are linearly independent set. So definitely a1j, amj, these are 0. Now if we change alpha j to any vector, ultimately that means varying j equal to 1 to n, we get all the coefficients a11, a1n, these all are 0. So this set of linear transformations u11, u1n, e21, e2n, this is also independent, and hence this forms a basis for LVW. So dimension of LVW equal to Mn, because there are Mn number of transformation. Next theorem on the composition of transformation. Let F be a field, V, W, Z be 3 vector spaces over the field F. Let T and U, T be a linear transformation from V to W, and U be a linear transformation from W to Z. Now we define the transformation UT from V to Z as UT of alpha equal to U of T alpha for all alpha belongs to V. Then the conclusion is that this defined mapping is a linear transformation. It is also easy task. I may leave it, but do it here. Let alpha beta be 2 elements in V and C be an element of F. Then UT of C alpha plus beta equal to U of T of C alpha plus beta. Now T is a linear transformation, so this is equal to C T alpha plus T beta. Again U is a linear transformation, this is equal to C into U of T alpha plus U of T beta. Again U of T alpha means UT of alpha, UT of beta. So this equal to this means UT is a linear transformation. Now if we take both the vector spaces V and W are same, so any linear transformation from T from V to V, this is called an operator, linear operator. We give a new term. Now we have some observations. Let F be a field, V be a vector space over the field F. T and U are two linear operators. In this case, TU and UT both are defined as in the previous theorem. But it does not imply UT equal to TU. Okay, because sometimes they may be equal, but sometimes they, so in general they are not equal. They are not commutative. Next, we can define the power of T, that is T square means T of T, T cube means T square of T. In this way, T to the power n from V to V, these are linear operators. And also T to the power 0 will be taken as the identity operator. Okay, we have this lemma: F be a field, V be a vector space, U, T1, T2 be 3 linear operators on V. Okay, C be an arbitrary element in F. Then number 1, IU equal to UI equal to U. You can prove it. U into T1 plus T2 equal to UT1 plus UT2, T1 plus T2 of U equal to T1U plus T2U, C into U of T1 equal to CU T1 plus U equal to U of CT1. That means LVV, this vector space, together is an algebra, okay, together with these operations, because it has some vectors space operations and these operations, together with these, this forms an algebra. This is called the linear algebra, LVV. Okay, now invertible function, look at this. It is function. First I am giving the term, it is not transformation. Let F be a field, VWT, V and W are vector spaces, T be a linear transformation from V to W, then T is called invertible function. Invertible function if there exists another function from W to V such that U of t it is the identity transformation on V, IV, and T of U is the identity transformation on W, that is IW. In this case, T is called the U is called the inverse of T, and U is written as T inverse. Now we have some observations. We know that T is invertible if and only if T is 1 1 and T is on 2. Okay, next theorem, let F be a field, V and W be two vector spaces over the field F, T be a linear transformation from V to W. Now T is invertible implies, means the conclusion, if T is invertible then T inverse is also a linear transformation. Look here, I am not saying that T inverse is a transformation. Here I am taking just it is a function. From this theorem we will prove that T inverse is also a linear transformation from W onto V. Okay, so how? T inverse maps W to V, be a function. We are taking beta 1, beta 2, b2 arbitrary elements in W, and then we get two unique elements alpha 1, alpha 2 in V such that the T inverse image of beta 1 is alpha, T inverse image of beta 1 is alpha, T inverse image of beta 2 is alpha 2. This is alpha 1. Therefore, T alpha 1 equal to beta 1 and T alpha 2 equal to beta 2. Now C be a scalar, so T of C alpha 1 plus alpha 2, this can be written as C T alpha 1 plus T alpha 2, because T is a linear transformation. T is a linear transformation, it is given, it is known. So this is equal to C into beta 1 plus beta 2. That means T inverse of this quantity equal to C alpha 1 plus alpha 2. Also this C alpha 1 plus alpha 2 is unique, so that it holds. Therefore C alpha 1 plus alpha 2 equal to T inverse of C beta 1 plus beta 2 implies T inverse of C beta 1 plus beta 2 equal to C alpha 1 means T inverse beta 1, alpha 2 means T inverse of beta 2. Therefore T inverse is a linear transformation. That's all for today.